This is the revision of the Engineering Science N4 paper that was written April 2026. So without wasting much time, let's quickly go into the revision. I'm skipping the instructions there for the sake of time and progress, but I do advise when you are in the exam, go through them and understand them very well. So I'm on question number 1 there, under kinematics 1.1 was saying, a submarine fires a torpedo at a freighter in the North Atlantic. The torpedo travels at 32 meters per second northwest. The freighter travels at 10 meters per second east, 60 degrees east of south. What is the velocity of the torpedo relative to the freighter? That's our question. Okay, so I'm going to demonstrate both two methods that we can use to answer this question. Right, number one, I'm going to draw a triangular diagram for the first method that I want to demonstrate. Right, this is the direction that the torpedo has taken, which means it's traveling at north west, which means northwest here, there's 45 degrees. Right, of course, and even here as well, there's 45 degrees. So it's good just to note that. Right, then the freighter travels at 10 meters per second, 60 degrees east of south. So that means 60 degrees east of south. East of south is this direction here. This is east of south. So they are saying 60 degrees east of south, which means this is 60 degrees here, east of what? Of south. That's the direction. Right, so one thing now to just join these two here. I'm going to join with something similar to this, right? Of course, my diagram there is a little bit poor, but let it be known that it is in this form. This is the diagram that we are supposed to bring out, of course, right? So there we go, right? So I'm just going to indicate again the other cardinal points here at this point. I'm going to indicate again other cardinal points at this point. So this is our north. This is our north here. So is this our south. So of course, understanding again, this is west and east. Oftentimes people have a problem in identifying west and east. So let it just be known that you just have to know, up north, we don't have a problem, down south, don't have a problem. West is to the left and east is to the right. And so you just say we. It's much easier to relate with that idea in mind. Okay. So here is our triangular diagram. Now, with this diagram that we have, the torpedo was going in this direction. What was the velocity of the torpedo? That was 32 meters per second. And then the freighter, what was the velocity of the freighter? That was 10 meters per second. So this is what we have. Okay, so what is the angle within the triangular diagram? So it might seem like it's not really a triangular diagram. It is the triangular diagram. We have this angle here, this angle that I'm indicating here inside. We can know the size of this angle. What exactly is the size of this angle that I've just indicated? Okay, first we have this is 30, right? And then we have this is 90. How do we know? We know that between all the cardinal points, this is a 90, these are 90-degree angles that we have here. These are 90-degree angles that we have. Then, of course, this is, so we said this is 45 plus 90 plus 30. So if we add that 90 plus 30, that's 120, plus 45, that's 165. So this whole angle here becomes 165 degrees, right? Now we want to calculate this length. Apparently, this is the magnitude of the velocity of the torpedo relative to the freighter, which apparently is going to be the same as the velocity of the freighter relative to the torpedo. The magnitude is the same, except the direction won't be the same. The magnitude is the same. So having that in mind, it means we can then easily calculate the velocity of the torpedo relative to the freighter. What can we use? We have side and a side, we have a side again, we have an included angle. So we use cosine rule for such a situation. Cosine rule simply states that a squared is equal to b squared plus c squared minus 2bc cos a. That's what it says, right? So with that in mind, we can safely just say 32 squared plus 10 squared minus 2 times 32 times 10 cos 165. Now, here is the important part. In using this method, first things first, we ought to know this formula by head. We have to just know it. And then, of course, how then do you know this is your B, this is your C? It doesn't matter. You just have to know that of the two sides that you have been given. Remember, we are saying we have a side We have a side, and then an included angle. So with that which we are having, you ought just to know that of the sides that you have, that's where your B and your C are. And it doesn't matter which one. So even if I had said 10 squared plus 32 squared minus 2 times 10 times cos times 32, I was still going to get the same answer. There is not a problem on that. Okay, so if I then punch this on the calculator, it's going to give me 1,742 comma 197,529. Right, so apparently this is squared as a matter of fact, because this is a squared. Okay, so square root of that value is now going to give us 41,739,579.85. So to 3 decimal places, that is going to give us 41,74 meters per second. That's 3 decimal places. Of course, so it's 41,740 meters per second. So we have determined the magnitude, which means we now have the velocity of the torpedo relative to the freight. We have the magnitude. But we want also the direction, because the moment the instruction says determine the velocity, we know that velocity is a vector. And since it's a vector, we need magnitude as well as what? Direction. That's what we know. So we want direction as well right now. So here is the clue when you are using this method. You can say, if the instruction is to say, determine the velocity of the torpedo relative to the freighter. So it's with respect to the freighter. We are at the freighter. Remember, this is the direction that the freighter is taking. This is the direction that the torpedo is taking. So we are at the freighter here. We want to know what is the direction of the torpedo when we are at the where the freighter is going, when we are taking the direction of the freighter. So already we can see that from the freighter's perspective, or from where the freighter is, the direction of the torpedo is north towards west already. Before we even perform any calculation, it's north towards west, or we can say west towards north. It's still one and the same thing. We are saying it's this direction here. It's this direction, right? So what we want to do right now is we can find this angle, or we can find this other angle here. The onus is on us. If we find the bottom one, which is this one, we are saying west towards north. If we find this one, we are saying north towards west, right? So how can we find it? We use this angle. We use this one, the one in between this one. That's the one we can use. So how do we use it? We simply calculate from the triangle, of course, that we are having. We can use sine rule from there. So what does the sine rule say? It says sine A over A is equal to sine B over B, right? So in this scenario, sine A becomes our unknown angle, the one we have just marked there. That becomes our sine A. That's the one we are having as our unknown angle, right? So it's opposite to which angle? That is it's a small a. So it's sine A, our unknown. I'm just gonna push this aside a little bit. Okay, so sine A over 32, which is this side, it's the one that is opposite to this angle, is equal to, right now we have just determined this as 41,74, so we are taking that advantage. So we are saying sine 165, the angle, over the side opposite to it, which is going to be 41,74, right? So making A the subject, sine A is equal to 32 sine 165 over 41,74. So that's cross multiplication, of course. So I just multiplied by 32, multiplied by 32. So let's not waste time. Remember, 1 to find sine, to make sine A the subject. So it means, therefore, A is equal to arc sine. Arc sine of what? Of 32 sine 165 over what? Over 41,74. There we go. So what do we get here? We get 11,445 degrees. Where is that 11,445 degrees on our diagram? Remember, we said our quest right now was to find this angle. We just got it. This is the angle that we have just determined right now. This is our 11 445 degrees, right? So, but then before we calculated this angle, this whole angle here, this one, this angle, I will try to increase this so that it's quite visible. This angle, it's not. How do we know it? Remember, these are not things. This line and this line, these are not things that we have, and all not things are parallel to each other. Meaning, if this angle here is 60 degrees, so is also this angle that I have marked in green. It's also 60 degrees. This one is 60 degrees. If this angle here is 60 degrees, so this one is also 60. Why? Because these are alternate angles. So out of that 60 that we have, subtract the 11.445 that we have just determined. It means we are left with 48,555. What is that one? That's the angle remaining, this one. So it means our direction, we now have it. What is then our direction? Our direction becomes north 48.555 degrees west. That becomes our direction. Or we can say west, what? West, right? 90 minus 48.555, we get 41.445 north. It's basically one and the same thing. Therefore, the value of our velocity is now found. We have it. Now, what is it? It is 41.74 meters per second. West, 41.445 degrees north. Or we can say north, 48.55 degrees west. We are still fine. The onus is on us, right? So this is one method we have used to determine the velocity, right? Option 2, I also want to demonstrate using the other method. How were we supposed to do it? So with the other method, right, I'm just gonna erase this to demonstrate it as well here. Okay, so here is what we can also do. Number one, we will choose certain directions for the two directions, dimensions that we have, the vertical dimension and the horizontal dimension. I'm going to choose one direction for each. So I'm going to take north as positive for the vertical and east as positive for the horizontal. So for the vertical, I have taken north, and for the vertical, for the horizontal, I have taken east. Who is telling me to do this? No, we have to know these are vectors we are dealing with. Vectors, velocities are vectors. So as long as you are dealing with vectors, you are dealing with something that has a direction. So you ought to choose one direction as positive, of course, when you are dealing with it. So that's what I've just done. Okay. Now, from the same information, I want now to draw the diagram of the torpedo. Of course, we have seen that the torpedo took this direction, and we already know this is 45 degrees, and this is north, right? So, how are we going to perform the calculation, right? Starting first with the torpedo, we want the vertical component of the torpedo. I'm going to label it as VTY. That's the vertical component. So the vertical component shall be given by, okay, here is what I'm doing. We'll try to use a different font, right? From the tail towards the head, that's where I'm going. So I will move in this direction. There I go until I'm aligning. So this is the direction. This is marking VTY. And again, this is now marking VTX. What I'm doing is already telling me the direction. VTY is going upwards. VTX is going to the west, right? So let us start with the VTY. It's going to be 32 cos 45. Why cos 45? Because, of course, this is the right angle triangle that has been formed here. As I move from the tail to the head, I have taken which direction is positive. I'm going, of course, that's a right angle triangle that has been formed there. And I'm going, of course, to the north. And I took north as positive. Remember, I took north as positive. So for that reason, it means even my VTY here, the vertical component of the velocity of the torpedo, is already positive. That's what it means, right? So 32 cos 45 is what I'm now calculating. That's 0.627 meters per second. The question is, what if I had done it this way? What if I had taken this, which means this is my horizontal component VTX, and this is my vertical component VTY? Was I going to get a different answer? Of course I wasn't. I was just going to use my theta as this angle now, and this is then another right angle triangle I would have formed. Still fine. I'm moving from the tail to the head. It's still one and the same thing. But mind you, my vertical component is what? Positive. You see that? It's positive because it's going upwards. So I will just label it as positive here so that you can see why, because I chose north as positive and it's also going to the north, therefore it's positive for that reason. In the same token, I'm going to calculate as well VTX. I'll calculate VTX as well, right? So for VTX, what am I going to do, right? Assuming I'm using this diagram that is above, that's my 45-degree angle there. So I'm going to say 32. Remember, that's my torpedo. The velocity is 32 here. So 32 sine 45. Why? Because this is opposite and this is my hypotenuse. So the ratio that I'm supposed to use is sine for that reason. But what if I had taken this diagram that is at the bottom here? What was going to be my VTX? Of course, it was going to be given by cos of this angle. And unfortunately, the angle is still also 45 degrees. Or should I say, fortunately, the angle is also still 45. But if this one was 60, it means this one was going to be 30. Or if this one was 50, this was going to be 40. Why? Because this whole angle is 90 degrees. Right? So 32 times sine 45. What do we get? Still, we are going to get the same value. But mind you, which direction are we taking? We are taking the west as the direction we have taken. But what did we choose as positive? We chose east as positive. Therefore, it means this is negative. Negative what? Negative 22.627 meters per second. Now you see where the negative is coming from. It's coming from the direction that we are taking from the tail towards the head. So in that way, in that regard, we have now the vertical component and the horizontal component of the velocity of the torpedo. Right, let's go to the freighter. So I'm now going to the freighter. We'll calculate. I'm also going to draw the diagram here. Right, this is where the freighter is going. Remember, it went 60 degrees east of south. So this is our south. This is the east. So it's going 60 degrees east of south. There it is going. That's the direction it has taken. Right. So with that in mind, remember it's 10. Velocity of the freighter was 10. So with that in mind, I now want to indicate the two components of the freighter. I'm taking this direction here, this one and this one, from the tail to the head, from the tail here to the head here. That's where I'm going. So it means this is the direction I am taking. This is the direction I'm taking. A right angle triangle has also been formed. So this is now forming my VFX, and this is now forming my VFY. I'm labeling one VFX, I'm labeling the other one VFY. The choice is mine. Okay, so even if you say horizontal component, VFH, VFV is the vertical component, the eyes upon you, there's no problem on that. Okay, so let us now calculate VTY. VFY, the vertical component of the freight, is going to be given by what? Look at the diagram that I have taken. I have taken this other diagram here, this one, which means this angle is no longer 60, this one. What size is it? It's 30. Where am I getting that? I know that this whole angle is 90 degrees. That's the advantage I'm taking. So that's 30 there. Okay, so what is the size of VFX? VFX, therefore, is going to be given by 10. Cos what? Cos 30. Where is that coming from? It's coming from the fact that this is adjacent, right? And this is the hypotenuse. So the ratio that has adjacent and hypotenuse at the same time for VFX, it's which ratio? Cosine ratio. So that's where it is coming from. Alternatively, I could have taken this direction here, this one, meaning this is my vertical component and this was going to be my horizontal component. So my VFX was going to be given by opposite and hypotenuse, which is sine. So I could have said 10 sine 60, I was still going to get the same answer. What is that answer? The answer is in for VFY, that's in for VFX, sorry, that's in 8.660. I'm punching the calculator there. This is what I'm getting. But is it positive or negative? It is positive, obviously. Why? Because I took, which direction did I take as the, so I'm calculating VFX right now. VFX is what I'm calculating. Let me just change that here to make it VFX. VFX is the one I'm demonstrating. So this is VFX, pardon for that. This is VFX that I'm indicating here. So I am saying it's 10 cos 30y because this is my adjacent while this is my hypotenuse. So I could have said 10 cos 30, or I can say 10 sine 60 if I use this direction. So this is my VFX, while this is my VFY, because this is the vertical component. It's vertical, while this is horizontal, right? So I hope that didn't lead us astray there. The mistake that I just did, but I'm just correcting that. This is VFX that I'm just calculating there, right? So I've just calculated VFX, and it's this size. And it is positive. Why is it positive? Because I took east as positive when I was choosing. Why did I do that? Because these are vectors we are dealing with, and we ought to do that. We ought to choose one direction as positive. So I'm now going to VFY now, the vertical component, which is either this one or this one. So sticking to one diagram, I'm using this diagram, mind you, I'm using this triangle here. That's the one I'm using. So with that triangle, we are saying, how do I calculate VFY? I'm going to calculate VFY by saying 10 sine, because this is now opposite. So I'm saying 10 sine what? Sine 30, because this is now opposite, while this one is hypotenuse. You get the sense? So it means this is now 10 sine 30. Or we could have said, if I was to use this other diagram here, this one, this triangle here, this side, it's also a right angle triangle. I was going to say 10 cos 60. I could have said 10 cos 60. I was going to get the same answer, cos 60 here. I was going to get the same answer. What answer is that? Right. This answer is -5. Where is the negative coming from now? What did I take as positive? I took north as positive. But from the look of things, my VFY is going downwards. It's going downwards. My VFY is going downwards. So for that reason, it's going to be negative because it's opposing the direction I took as positive. Okay. Now I have them all, the vertical and the horizontal components of the torpedo, the horizontal and the vertical component of the freighter. I have them. Right. So with that in mind, I now want to calculate the velocity of the torpedo relative to the freighter. That's what I want to calculate. The velocity of the torpedo relative to the freighter. Now, the method that I'm using, let it be known that whenever you are calculating the velocity of one object with respect to another or relative to another, you have to know velocity of A relative to B is equal to VA minus VB. The velocity of X relative to Y is equal to Vx minus Vy. That's what it means. Meaning to say the velocity of the torpedo right now relative to the freighter is equal to Vt minus Vf. This is a formula that you have to know, you have to understand. Unfortunately, you won't be having it on the formula sheet. You have to understand this fact. As long as you are calculating relative velocity, you have to know this. Okay, so with that in mind, it means it's taking us to something important. Let us start with the horizontal components. So I'm gonna call them this the sigma of the horizontal components, or I'll just call it Rx. So it's gonna be given by Right now, I am looking for the horizontal component of the velocity of the torpedo relative to the freighter. That's what I'm looking for right now. So, okay, so for it not to be confusing, let us call it the velocity of the torpedo relative to the freighter, x, the horizontal component of it. Right, so it's going to be given by Vtx minus what? Minus V T what? VFX, right? There we are. So what are we going to do? We take the horizontal components on their own. Let us check them. We are checking for the summation right now of the horizontal components, right? So let's check VTX. What did we get for VTX? We got minus 22,627. This is what we were having. Minus VFY, what did we get? We got 8. That's a positive, right? Positive. What if it was negative? We're going to say minus, minus, right? So it's 8,660, right? So what do we get if we simplify that? We get negative 31,287 meters per second. This is now serving as the horizontal component. So of what? Of the torpedo relative to the what? To the freighter, the velocity of torpedo relative to the freighter. So there we are. Let's go to the vertical components. The vertical component is the one we want now. So it's also going to be given by VTY minus VFY as well. Okay, let's go to VTY. Our VTY is 22,627, right? Minus our horizontal component, our vertical component of VFY is -5. So we say minus 5. There we are. And that is going to give us what? It's going to give us 22,627 plus 5, because it becomes a positive here, minus, and that will give us 27,627 meters per second. By the way, there's something very important that has just happened. If you look at the first part here, this one, we said it came out as negative 31.287. Already that is telling us a direction. What did we choose for the horizontal? What did we choose as positive? We chose east as positive. Meaning to say the mere fact that it came out as negative, it means it's going to the west. Same applies with this one, the horizontal, the vertical components, VFY. It came out also as what? Positive. And what did we choose as positive? We chose north as positive. So it means this is going to the north. We already have the direction, right? You see that? So once we have done that, it means when we now want to calculate the last, which is the velocity of the torpedo relative to the freighter, it's obviously going to be given by the square root of the horizontal component, squared plus the vertical component. What is our vertical component? Squared, right? So we simply take what we have right now, which is negative 31, 287 squared, right? Plus, what do we have also? 27.627 squared. What do we get? We get 41.739. We are still arriving at the same answer, 41.739. So of course, 39. So just because of the rounding off of the figures that was happening along the way, it slightly gave us a different number. That time we got 41.74. When we use the other method, now we are getting 41.739. Basically, it's one and the same thing. Now, when we want the direction, we take the north and the west to now create the resultant. Here is what we are going to do. It means this is the velocity of the torpedo relative to the freighter, the vertical component. And it's north, of course, from what we witnessed there. And what about the horizontal? The horizontal is west. So this is the velocity of the torpedo relative to the freighter, the horizontal component, which means the resultant velocity of the torpedo relative to the freighter is here. This is where it is. So we have an option of finding either this angle or that other angle here, this other one. The choice is ours, this one. So, of course, it's normally advisable to use the angle to the horizontal, which is this one, the angle to the horizontal. So that angle to the horizontal, I'm going to refer to it as theta. It's given by arctan of the vertical component over the horizontal component, right? The vertical over the horizontal. So directly we can simply say, if we want that angle theta, we can simply say arctan of what is our vertical component right now is 27.627 over our horizontal component. What is it? 31.287. Why am I ignoring the negative? Remember, the negative was only there to tell us is it west or east. The positive was only there to tell us is it north or south. So I would advise when you are performing this calculation here to put it aside. There is no need for you to use it. So when you do that, you get 41.445 degrees, and apparently it is the same with what we got on the other method. So already it means this is west towards what? Towards north. Remember from our cardinal points that this is north and west already. So it's west towards north. So our angle becomes west 41.445 degrees north. We are still arriving at the same exact answer. The choice is also ours. So this is one and the same thing, right? So it's pointing really that all roads will lead us to Rome. Let's go to the next question. The next question number 1.2 is saying an aircraft is at Vanderboom International Airport and wants to fly to Lanseria Airport, which is 70 kilometers to the south. If the aircraft can travel in still air at 200 kilometers per hour and the southwesterly wind of 50 kilometers per hour is blowing, calculate its resultant velocity if the pilot aims south. I'm going to do it again with the two possible methods that we can still use. The triangular diagram for the first method, we can safely just say these are the cardinal points that we have. North, of course, there is south, but then we are told that the aircraft is going south. So we just proceed down. There it goes. Right, there it goes. Then we are told that there's a southwesterly wind of 50 kilometers per hour, and apparently the plane is going at 200 kilometers per hour. So I'm just going to label this VP, the velocity of the plane or the velocity of the aircraft. Right, then along the way, we are saying there is now a southwesterly wind. So, winds are named according to where they are coming from. So it means if it's coming from southwest, where is it going? It's going northeast. This is the direction that the wind is going. So there is our wind. So, of course, we know that there's an angle of 45 degrees. So is there also 45 degrees here, 45 degrees here. So is also 45 degrees. That's what it means. So then what we do now is we just draw a line from the point of the departure of the plane towards the line of the wind, where the wind is going, right? That's now marks our RV, the resultant velocity. So this is the velocity of the wind. Apparently, we're told it's 50 kilometers per watt per hour. Now, with that, we have created a triangular diagram. So there's a 45-degree angle there within our triangular diagram, right? So with that in mind, we now want to calculate RV. Again, we can still use the formula A squared is equal to B squared plus C squared minus 2BC cos what? Cos A, our cosine rule, right? So with that, it means this is our RV is the A, the unknown. RV squared is equal to B and C, doesn't matter which one, between 200 and 50, whichever you start with, you will still be fine. So 2 times 200 times 50, right, cos 45, that's the angle between them. So that's cos 45. There we go. That now marks our, so with that, if we punch that, we are going to get 28357, that's 28,357.86438. Right. That's the square of our RV. Right. What about the square root? The square root of that value is obviously going to be the square root is 168.398 to 3 decimal places. That automatically marks our RV. So this is now our resultant velocity, our resultant velocity. We have determined it. Right, looking at now the angle, this is the angle that we want. Right, automatically it means RV right now is going in between east and south. So all we want is the angle south, our main degrees east, or east, our main degrees south. We want to calculate this angle here. We can still use the sine rule. In what sense? In the sense sine A over A is equal to sine B over B. Right, so now we have RV, the resulting velocity, we got it as 168.398. We got it as such, kilometers per hour. So it means we can use sine rule. In what sense? Sine A over 50, that's the angle, that's the side opposite our unknown angle, over 50 is equal to sine 45, sorry, over 168, right? Multiply by 50 there, multiply by 50. It means we are now left with sine A is equal to 50 sine 45 over 168. So A is equal to arc sine of 50 sine 45 over 168. There we are. So arc sine of that value, we get 12.1198. So 2 decimal places, that's 12.12 apparently. So that's 12.12 degrees. Right, what is that angle? This is the angle that we've just determined, this one, 12.12. And indeed, it can give us our direction south, 12.12 degrees east, or we can say east. What is the size of this remaining angle here? Subtract that from 90. Subtract 12.12 from 90, we get 77.88 degrees south will still be correct. So we can safely say that's 168.398 kilometers per hour. How many degrees east? 77.88 degrees south. So the onus is on us. We can use this one, or we can use this other one. We will still be fine. So this is now marking our resulting velocity, method 1. This is the first method that we have used. Now we are saying, is this the only method that we could have used? No, unfortunately, we could have also used another method. Let us try with the other way. So alternatively, we could have said, to determine that, okay, we'll choose again our one direction. We'll choose our directions again. Let east be positive and north be the positive for the horizontal and for the vertical. For horizontal, we have chosen east. For vertical, we have chosen north. It's our own choice. Right, then we now want to find the horizontal components and the vertical components of the plane and as well as the wind. So let us start with the plane's components, the components of the plane. Right, remembering or bearing in mind that the plane is going due south. The plane has gone due south. We have understood that. Right, so with that in mind, it means it's telling us that let us start with the horizontal VAX. The horizontal component of the plane is obviously going to be given by 0 kilometers per hour, right? Because it went due south. Then VAY is going to be given by negative 200 kilometers per hour. Why is it so? Because we chose north as positive, yet the plane is going south. No need to perform a calculation for that. You can easily notice it without performing a calculation. Let's now go to the wind components. So with the wind components now, we are saying VAX is equal to, VWX, on that. We are saying VWX, the horizontal component of the wind, right? I want to demonstrate it using the diagram. So I'm going to demonstrate a diagram here. We say the wind came from southwest, but it's not going to southwest, rather it's going now where? To north. Well, this is north here, and this is east here. So it's going to northeast. So there's a 45-degree angle here. So it's also a 45-degree angle. If I opt to take this direction here, this is my horizontal component. And then I take this direction here. This is now my vertical component. So this is now marking my VWY, while this is marking my VWX. Right, just like that. So VWX is equal to, from the look of things here from the diagram I've just drawn, it means it's given by, what is the wind? The speed is 50. So it's going to be given by 50 cos 45 from the diagram. So it's known. We can also use this other root here. The choice is ours. So 50 cos 45. And we are going where? To the east. So it's positive. Therefore, it means it's positive what? 35.355 kilometers per hour. That's marking our VWX. Now let's go to VWY. VWY, the horizontal, the vertical component. So it is this one now, opposite and hypotenuse there. So that is 50 sine 45. Apparently it's going to give us the same value again, 35.355 kilometers per hour. Okay. Is it positive or negative? It is positive because we are taking upward direction as we are going. So it means we chose north as positive. Apparently it's also going to the north. Okay, now, in order for us to calculate the resulting velocity using this method, number one, we need the horizontal and the vertical components. So I'm going to call one Rx and I'm going to call the other one Ry as the resulting velocities. Now, so for the resulting velocities, you add the respective components together with their corresponding signs that they are having. Right now, these ones are positive, but we notice this one, of course, is 0. Then this one is negative. You see that? So you are adding them, not forgetting that these are vectors. So you have to add them considering the fact that they are vectors. Let us start with Rx. So Rx is going to be given by V AX, the V plane, the plane, which is our aircraft. I'm using it as VA there. Right, so VAX plus what? Plus VWX. So what was VAX is 0 plus VWX, that's 35.355. So if we add that, we end up having 35.355 kilometers per hour already, simply because it's coming out as positive. It's already telling us the direction. What is the direction? The direction is east, because we chose east as positive. Hence, it's coming out as positive. It's already telling us that its direction is to the east. Let us go to RY. RY, the resulting component of the vertical components, is going to be given by VAY plus VWY. Okay, so what is our VAY? That's negative 200. That's the one we had there, plus. What is our VWY? We got it again as 35.355. So adding these two, they end up giving us negative 164.645 kilometers per hour. That negative alone is telling us the direction. What then is the direction? What did we choose as positive? We chose upwards as positive, and we chose north as positive there when we started. So it means this is south. The vertical component is obviously going to the south. So it means we have also drawn the conclusion for the vertical components. It is to the south. So this one is south. Okay, with that in mind, it means we can now be able to calculate RV, the resulting velocity, with this method. Therefore, RV is equal to the square root of Rx plus Ry. And therefore, this is 35.355 squared plus negative 164.645 squared under the square root. And that in turn is going to give us 168.398. We are still arriving at the same answer, 0.398 kilometers per hour. It's basically one and the same. How about the direction? We got east for Rx and south for Ry. So we shall draw them as such. There is our Ry going downwards. There is our Rx going to the east. It means at the center is where we are now drawing our RV, the resulting velocity. So this is where it's going. So we have an honor of either calculating this angle or calculating this angle. I'm referring to this one as alpha, while I'm referring to this one as theta. Theta is the angle to the horizontal. That angle to the horizontal is always given by arctan of Ry over Rx. It's kind of straightforward. This is a right angle triangle, mind you. The right angle triangle we have is this one. So with that, we are saying this is our Rx, so is this our Ry. Opposite over adjacent, that's tan. So that's why we are using tan. Had we opted for this other angle, which means this one here, this other triangle, I mean, it means this was our Rx and this was our Ry. Opposite becomes Rx, adjacent becomes Ry. So we say arctan of Rx over Ry. We will be getting this one. We will be getting this angle. And unfortunately, I'm saying I want to use this one, the angle to the horizontal, not the angle to the vertical. So the angle to the horizontal is going to be given by arctan of, right, our Ry. We got it as negative 164.645 over Rx, we got it as 35.355. Right, so with that, it means it's giving us 77.881. Right, we are still arriving at, so it means now with the angle that we have already, this is east, while this is south. So we are saying east towards south. How many degrees towards south? We just got the angle now. So it means it's east 77.881 degrees south, which means we are still arriving at the same answer that we got the other time. So it means our magnitude is 168.398 kilometers per hour, east 77.881 degrees south. So the onus is on us. If we now decide to find this other angle here that I have referred to as alpha, it means we are now saying south how many degrees? Now, if we say 90 minus that angle, of course, we end up having say 12.22, something like that, degrees west, right? So it's still another option again, which is still proving that we can still arrive with the other method as we did with that other method. So basically, this is how we do it. So moving on, having understood this part, it takes us to the next question, which is question number 2. Question number, sorry, 1.3. That's the question we want to go to. Okay, question 1.3 saying an archer shoots an arrow at an angle of 30 degrees to the horizontal at a velocity of 280 meters per second. Calculate the following: the time it takes to reach its maximum height, right? The moment we talk of the maximum height, we are talking of the vertical motion. So for vertical motion, we need to find the initial velocity for the vertical component. It's given by u sine theta. So in our case here, since it was shot at 280 meters per second, it means we can say 280 multiplied by sine what? By sine 30. And that in turn gives us 140 meters per second. That means that's our UV. Right, so since we want the time it takes to reach the maximum height, that's T max. We can call it the T V max, the maximum height time. It's gotten from the formula, the equation of motion. V is equal to U plus AT. And of course, these are projectiles. This is a projectile that has been shot. The arrow becomes a projectile. So it means A is known, A is G, the gravitational acceleration. So making T the subject, it means our formula can say V minus U over G. That's kind of straightforward. V is equals to U plus GT. Remember, our A is known, is now G. So if we now make T the subject, V minus U is equal to GT divided by G. Hence, we come up with this formula. So V, the velocity, the final velocity, at the maximum height velocity is known. What is the velocity at the maximum height? It's 0. So 0 minus the initial velocity. The initial velocity is going to be what? UV. This is the initial velocity that we are going to use. So what is it going to be? It's going to be 140 over the gravitational acceleration. Now, at every given time, gravitational acceleration is acting downward. So it's negative 9.8 because we would have taken upwards as positive. Hence, that's why our initial velocity, our initial velocity here is going to be what? It's going to be 0. It's going to be negative. So with that in mind, we end up having 14.286 seconds. That becomes our time. There we go. Let's go to 1.3.2. The maximum height it will reach. Right. With the maximum height, we still can use the equations of motion. What are the equations of motion saying? They are saying V squared is equal to, of course, U squared plus 2AS. This is the other equation of motion that we can use apart from others. We can use this one. Making S the subject, it means S is going to be V squared minus U squared over 2A. But remember, A, we know it is G. So we can say over 2G and it will still be fine. So with that having been said, we can therefore safely substitute that into the formula. S max, the maximum height, is equal to V squared minus U squared over 2G. What is our V? It's 0. Squared is 0 minus 140 squared over 2 times negative 9.8, and that in turn will give us 1,000 meters. Option 1. Option 2, we could have just used the formula S max is equal to U squared sine squared theta over 2G, right? It's another formula for every maximum height. If ever a question comes asking you maximum height, you can actually use this formula here. U squared sine squared theta over 2g, and you'll still be fine, right? Let's go to SH, the horizontal distance. The question is saying, calculate the displacement of the R when it hits the ground. That's the horizontal that we are now calculating. So with that, SH can be calculated by the formula UH multiplied by TH. So we need to first calculate UH, the horizontal initial velocity. It's given by U cos theta. This is the formula. So we can safely say 280 multiplied by cos 30, and that gives us 242.487 meters a second. That's UH, right? Then we want also TH. Apparently 2H is equals to 2 multiplied by TV, the time taken to reach the maximum height. So we simply take that time taken to reach the maximum height, 14.286, and multiply it by 2. We get 28.572 seconds. That becomes the time for the displacement, the range. So with the 2, we can then calculate SH. So SH is now going to be given by, therefore, SH is equal to 242.487 multiplied by 28.572, and that in turn gives us 6,928.339 meters. We could have arrived right here. Alternatively, we could have used the formula again. SH is equal to SH is equal to U squared sine 2 theta over G. Right, whenever you use this formula, just like the other one I did mention of U squared multiplied by sine squared theta over 2G, don't consider the gravitational acceleration as a vector, as I was doing on this other formula. You just substitute directly the way it is. You just substitute the way the values are. U, the way it is, 280 squared times sine 2 theta, your theta that you have been given. Then you just go straight to the answer. Okay. These formulas are good when you don't have t the time. It's quite good to also use it, unless of course if you would want to calculate t like what I've just done, the onus is on you. Okay, so that basically takes us to 1.3. Okay, with 1.3, let us then go to question 2, the angular motion, right? Angular motion question. 2.1 is saying the wheel of a motorbike has a diameter of 750 millimeters and rotates at 105 revolves per minute. Calculate the following: the angular velocity of the wheel in rad per second. Right. Angular velocity omega is given by 2 pi n, where n is the rotational frequency and it must be in revs per second. Apparently, we have been given here n in revs per minute, so we would want to calculate it, to change it first to revs per second. What is it going to be divided by 60? 105 divided by 60, and that in turn gives us 1.75 revs per second. What we just done, we have changed our rotational speed to revs per second, because that's what is supposed to be used on the formula. So therefore, we can say 2 pi multiplied by 1.75, and that gives us 10.996 rad a second. As a matter of fact, angular velocity is measured in radians per second. So that's our omega there. Alternatively, we could have just done it once. Omega is equal to 2 pi multiplied by 105 over 60. In the same formula, we could have just calculated it once off. Okay, let's go to the speed of the motorbike. The speed of the motorbike, V, is equal to, this is now the linear speed, the linear motion, the speed for the linear motion. V is equals to omega times r. R, where r is the radius. What have we been given here? We have been given the diameter. So again, now that we have omega, we can just say directly 10.996 multiplying, right? Our diameter that we have is 750 divided by what? By 2 multiplied by 10 to the power of negative 3. Why am I doing that? It's in millimeters. We want it in meters. So we multiply by 10 to the power of negative 3, or we simply divide again by 1,000. We'll still be fine. What do we get? We get 4,124 meters per second, which means that marks now our velocity. Okay, 2.1.3, the distance traveled in after 15 minutes. Distance is equal to velocity times time, but our time must be in seconds, while our velocity is in meters per second. So we have the velocity 4,124 multiplied by the time 15 is minutes. So how do we change it to seconds? We multiply it also by 60. That gives us 3,600 meters. It's now in meters. Our answer comes out in meters. Note that the time should be in seconds. It's very important to take note of that. Okay, 2.2.1. 2.2.1 takes us to a force of 500 Newton is applied to the end of the span. The perpendicular distance between the nut and the working line of the force is 45 centimeters. Calculate the torque on the spanner. T, the torque, is equal to force multiplied by R, the working line of the force. Right, so we need to simply substitute what we have. What do we have? A force 500 multiplied by the working line, that's 45 centimeters. Converting that to meters is going to give us 0.45. Where is that coming from? We simply divided by 100. So that's 0.545, and that in turn gives us 225 Newton meters. We have arrived. That marks our torque. Let's go to 2.2.2. The work done when the nut is turned through an angle of 45 degrees. Okay, so work done is equal to torque multiplied by theta, where theta must be in radians. Okay, so here we have been given our theta in degrees, 45 degrees. So we want to change it to radians. 180 degrees is equal to pi radians. Then 45 degrees is therefore equal to what? X radians. We'll create an equation out of that. 180 over 45 is equal to pi over x. Okay, so cross multiply 180x is equals to pi multiplied by 45, divide by 180, divide by 180. So it means x is equal to 0.7854 radians. So it means it's now in radians. So with that in mind, we can therefore calculate the torque. Torque is equal to 225. Work done is equal to, so we know we did calculate torque as 225. So work done is going to be equal to torque times theta. So 225 multiplied by 0.7854, and that in turn gives us 176.715 joules. It marks our torque. So this is the end of question 2, taking us to question 3. Right, so with question 3.1, define potential energy. Right, we define potential energy as the energy that a body possesses because of its relative position with respect to a reference plane and gravity. That's the definition we can give. Okay, 3.2, due to a gravity, a trolley with a mass of 0.26 tons moves from rest down an incline of 33 degrees to the horizontal plane. The tractive resistance is 1.05, 1050 Newton. Calculate the speed of the trolley after 65 meters. Okay, that's where we want to start from. And first things first, we may want to calculate the acceleration. F net is equal to ma. Okay, what are the forces that we have on this incline? Okay, we have the parallel gravitational force going down the incline. I'm going to write it as from the formula mg sine theta. That's our parallel gravitational force there. It's going down the incline. Right, then we, of course, happen to have the perpendicular gravitational force. This is the perpendicular gravitational force, Fg perpendicular. As a matter of fact, it's given by mg cos theta, of course. Right, I'll just point out the crucial ones. We have the parallel gravitational force. We have the attractive resistance that we've been given there. I'll label it as Fr. Right, so for our F net in the plane acting parallel to the incline, I will ignore the normal force. I will ignore it at the moment because we are talking of the parallel of the plane that is parallel to the dimension that is parallel to the plane. So it means, therefore, Fg parallel minus the attractive resistance is equal to ma. Remember, we are dealing with vectors, hence they have a direction. Or right now, I would have taken downwards as positive, hence my parallel gravitational force is positive there. So how do we calculate it? It's going to be given by 0.6 tons. That's multiply that by 1,000. That's 600 kgs. Multiply by 9.8, multiply by sine 33 is equal to, minus 1,050 is equal to m, the mass 600 times the acceleration that we apparently are looking for. So we'll simply say 600 times A, the acceleration. Okay, so if we multiply this, we get 2,152.478 is equal to 600 A. Right, there we are. Then divide by 600, divide by 600. So it means A, the acceleration is going to be given by 3,587 meters per square second. Okay, that's our acceleration. Now, using the formula v squared is equal to u squared plus 2as. The question had said determine the velocity, the speed. So we can use this formula to determine. So it's going to be given by the square root of u squared. It started from rest, so that's 0 plus 2 times 3.587 that we have just calculated, multiplied by the distance, which is 65 meters. And that in turn gives us 21.594 meters a second. That becomes our speed. We would have arrived. Okay, moving on to the next question. An object is on a plank that is 9 meters long. If the coefficient of friction is 0.25, how high must the one of the plank be lifted so that the object just starts to slide down the plank? Okay, I'll demonstrate again with a diagram on this one. I'll demonstrate with a diagram. Right, here is what we have. Here is what we have. There is our plank. It must be lifted up. And as it is being lifted up, of course, there is an angle here, assuming there's going to be an angle here. So here is what we end up having. We are supposed to have an angle here. Right, what we are being asked to calculate right now is this height. This is the height that we are being asked to calculate. Right, so we want to know how high the side of the plane must be lifted up, considering the fact that the plank is, of course, 9 meters long. So from that regard, we are saying probably the object is sitting right at this point here, because it will have to slide down the incline. Okay. First things first, we have been given this coefficient of friction. This coefficient of friction, mu, is apparently equal to tan theta. Why is it so? Why is this equal to tan theta, this coefficient? Okay, so I'll put back this object back where I had placed it yesterday. I demonstrate why is mu equal to tan theta. The reason is we have the parallel gravitational force, of course, here, which is given by mg sine theta. That's true. That's our parallel gravitational force. Then we have the perpendicular gravitational force here, which is given by mg cos theta. That's true again, mg cos theta. Right, we have the normal force acting up. Then we have this side, we have the FR, right? The resistive the resistance, the resistive force, right? It's given by what? It's given by mu n, mu multiplied by n. But n now, n is given by mg cos theta because it's equal and opposite to the perpendicular gravitational force. So it means, therefore, FR here is given by mu multiplied by mg cos what? Cos theta. Now that tells us that when F net is equal to 0, it means mu mg cos theta, which is apparently our resistive force, should be equal to the parallel gravitational force mg sine theta. These two should be equal. Dividing by mg cos theta, dividing by mg cos theta, it means mg and mg, they cancel each other. Mg and mg, they cancel each other. We are left with, of course, we are left with mu being equal to sine theta over cos theta. But summoning our understanding of identities, the trig identity, this is a quotient identity. And what is it telling us? It's telling us that mu is therefore equal to tan theta. Right, so if mu is equal to tan theta, it then follows that it means tan theta can also be determined by, we can find tan theta by saying opposite. Let's look at the diagram there. What is our opposite? That's h. H. Over the adjacent, of course, the adjacent there in this regard, we do not actually have it. So what is then going to be the diagram? We can find it saying 0.25. Okay, so we can use this tan theta then to calculate the angle. We can use the coefficient that we have to calculate the angle. So it's arctan of 0.25. And that in turn gives us 14.036. So to 3 decimal places, that is going to be 14.036 degrees, which means now we have our angle now. Right, so with the angle that we have, we can now easily determine the rest. Okay, what do we have from the diagram? It means this angle here, we have it 14.036. Right, but we want h, the height that our must be lifted. So with that, we can safely say opposite and hypotenuse, the 9 meters of the plank. So which ratio can we use? Sine theta is equal to h over the length of the plank. So sine 14.036 is equal to h, the unknown, over 9. So 9 sine 14.036, it is therefore going to give us h shall be equal to 2.183 meters. That can be the height now that our plank has to be lifted. Okay, this is marking 2.183. question 3. On to the next question. 3.4. A mass of 48 kgs is projected vertically upward from the ground for 17 meters and is allowed to fall back. Calculate the following: the gain in potential energy when it is projected. Right, so gain in potential energy, EP, is given by mgh. Right, so what is the mass? That's 48. And multiplying by the gravitational acceleration, 9.8, multiplied by the height, that's 17, and that in turn gives us 7,996.8 joules. Okay, then the kinetic energy, just as the object reaches the ground, right, it has to be known that the EP lost is equal to the EK gained. This is being EK gain. This is being taken from the law of conservation of energy. So we ought to know that the same potential energy that would have been lost at the top will be the same kind, will be, of course, the kinetic energy that will be gained at the bottom. So it therefore automatically means it's 7,996.8 joules. That marks our EK. Okay. Let's go to 3.4.6. 3.4.3, the velocity. So velocity is taken now from EK, which is given by half mv squared. So it means half mv squared is equal to EK 7,996.8. So substituting what we have multiplied by 48 v squared is 7,996.8. Okay, so this is 24, of course. V squared is 7,996.8. Divide that by 24, divide by 24. That in turn is going to give us V squared is equal to 7,996.8 divided by 24. What are we having? That's 18. That's gonna give us 333.2. Square root both sides. Now the velocity is gonna be 18.254 meters per second. That marks our velocity. Okay, question 4. Question 4 is saying state the law of moments. Okay, it simply states that the sum of clockwise moments about any point is equal to the sum of the anti-clockwise moments about the same point. That's the law of moments. Okay, going on to question number 4.2. Consider the cantilever shown in Fig 1 below. Answer the questions that follow. Okay, so this is our beam that we have been given. So of course, there is a distributed load, and there is a concentrated load here, right at this exact point. And apparently it is exactly at this one point. It is exactly at this 1 meter here. That's where it is indicated at. And then of course we have the 2 meters here, the 1 meter, 3 meters, etc, etc. Okay, this is what we are having, and this is C, this is D, and this is E. That's our diagram. So what I'm gonna do, I will indicate it here on this with a scale. Of course, we can use 1 centimeter to represent 1 meter, 1 meter there. Okay, I will try to be a little bit accurate in drawing my diagram. Okay, there we are. Right, so we said we have the 5 kilonewton per meter here, and we have apparently the last part, which is giving us the distributed load of 3 kilonewton per meter. Of course, then we have here, that's 8 kilonewton, right? 8 kilonewton. And then we said this is here 3 meters, right? This distance is 3. And of course, here we have 2 meters, we have 1 meter, we have 3 meters. There we are. Okay, so that's 3 meters here. And there is 1 meter. And then here is 2 meters. Okay, there we are. So we have A, B, C, D, and E. The first question was saying, calculate, okay, it was saying actually draw, okay, so here we are. The first question is saying, draw the shear force diagram. And of course, 4.2.2 say calculate the bending moment. Let us first start by the drawing of the shear force diagram. That's the question we are at. So using our ruler, we will simply extend these lines down. We shall just extend them using our ruler straight down. There they go. There they go. There they go. So with that, it means we are simply bringing down the same measurements that are down. We are bringing them, that are on top, we are bringing them down. That's what it will be. Okay. Right. We may want to know RA, the reactive force, the reactionary force here at A, because this is a cantilever beam is supported only at this point. So obviously that will be given by 5 multiplied by 3, the distributed load here, 5 kilonewton per meter. That's going to be 5 times 3 there, right? Plus 8 plus 3 multiply by what? By 3. And that gives us 32 kilonewton. We can do this somewhere aside. It's still fine. So now we have RA, the reactionary force, the reaction force. Okay. So the moment we do so, we can now draw our shear force diagram. Okay, so here is what we are going to do on the one that we have taken down. We want to maintain the same measurements that we have in there. Down, we have our A, B. So we have done that with the ruler. Okay, so first things first, we draw our line. Right. Once we have done so, the first one that we are starting with is the 32 kilometers for the reactionary force. So we have 32. Okay, so we shall start with 32 at this point here. There is our 32 kilonewton. Right, from 32, the next that we have is the 15, 5 times 3 here. That's 15 kilonewton. Right, so 15 kilonewton. So we subtract now 32 minus 15, and that is going to give us 17. Now, because this is distributed load, we will not draw it horizontally, rather we'll draw it diagonally. So we are drawing now our diagram there, combining up to this point. Remember, we have already gotten our measurements directly from the first, from the initial diagram itself. Okay, so we have our 17 there. Then from this point, now we have a concentrated load. Where we have a concentrated load, we indicate with a horizontal line. So we said here at this point, we have 17 kilonewton. Okay. From the 17, the next that follow is 8 kilonewton, which is this one. So we say 17 minus 8, that in turn gives us 9 kilonewton, which means the next point here is 9. So we indicate now, because it's concentrated load, remember, so we have to draw our diagram in this manner. until we are at this point. So we are saying there is our 9 at this point, 9 kilonewton. Right. Then from the 9, subtract 3 multiplied by 3, that's 9. 3 minus 3, so 9 minus 9, that's a 0 there. So obviously, this will give us a 0. So we want to come to this point. But we are not going to draw a horizontal line anymore. Rather, we are now going to draw a diagonal Y. There is distributed load there. So it marks our 0 point here. This is now our shear force diagram. So we have answered that 4.2.1, draw the shear force diagram. This is now marking our shear force diagram. Remember, we have taken the accuracy of the diagram from the diagram itself there on top. That's why it would be wise sometimes just to draw it if you want to. So we are extending our lines again down as we want now to draw the bending moments diagram where we are taking the information from 4.2.2, calculate the bending moments and draw the bending moment diagram. So we want to first calculate them and then draw them. I'm extending again. I'm extending it down. I'm extending down, bearing in mind that we have A, B, C, D, and E as our points. So we are saying this is our A here, our B, our C, our D, and our E. This is not necessary as a matter of fact. I'm just doing it so that we continue to move along together. There we are coming from here. Okay. So first things first, we want to calculate the bending moments. Right. So we want to first start with the bending moments at A. I'll just push aside here to indicate the bending moment, to calculate the bending moments here. So I will start with the bending moments at A. And the bending moments at A is going to be given by negative, right, 9 multiplied by 7.5. Where is that coming from? It's coming from the diagram here. So we are saying 9 multiplied by 7.5. Right, starting first with this, so we are saying we have agreed that this is 3 times 3, that's 9 here. Right, multiplied by what is the distance at the center here? It becomes 1.5. So this is 1.5. So if we add 1.5 plus 1 plus 2 plus 3, and that in turn gives us 7.5. So we have 9 multiplied by 7.5, right, minus, we go to 8. How far is 8 from A there? We see that there is 5 meters. There 2 plus 3, it's 5 meters. So with that, it's going to give us 8 multiplied by 5. Minus, we go to the last, that's, remember, this was 5 kilometers per meter. So it's going to be 5 times 3, that's 15. 15 times, right? What is the distance now from A, right at the center, here at the center? So this is 3 meters. So at the center is 1.5. So it's going to be 15 multiplying 1.5 times 1.5. And that in turn gives us minus 130 kilonewton meters. Right. So this is now marking our bending moments at A. Let's go to the bending moments at B. Right. So we'll start again. At B, this time around, B is in at this point. So start again from the furthest. 9. Our distributed load here. 9 multiplied by what is the distance? 1.5 plus 1 plus 2, that's 4.5. So it means, therefore, this is going to be 9 times 4.5. So like that as well. 8 times 2, and that is going to give us negative 56.5 kilonewton meters. Okay. Then let's go to the bending moments at C. So we move on to the bending moments at C. Repeating ourselves, it means it's 9 multiplied by 2.5, which is going to give us negative 32.5 kilonewton meters, right? And then bending moments at G, that's also negative 9 times 1.5, and that in turn gives us negative 13.5 kilonewton meters. So basically, we are repeating ourselves in the same fashion where we started from A, B, C, D, until we are at E. The bending moments apparently at E is going to be 0. So that marks the last one. Bending moment at E is 0, right? Okay, so we have calculated them. Now we want to literally use them to draw the bending moment diagram. So with that in mind, it means just drawing it, remembering this is a cantilever beam that we are. So starting first with our axis, there we are. And when indicating this is 0, so we'll say this is 0, 0 there. Okay. This is where we are. Right. Understanding that this was a distributed. Okay, this was a distributed load. So we shall indicate with a slight curve. There we are. Then moving on to this part. There we go. So we are saying this is where we have negative 130 kilonewton meters, and then this is where we shall have negative 56 kilonewton meters. And this is where we are going to have negative 22 kilonewton meters. And then again, we indicate this with the last part, and then the last part until we are at 0. By slightly having my diagram a little bit, we are having negative 18.5 kilonewton meters at this point until we are at the point 0 here. So this is how it is supposed to come out actually. Right, so most slightly open it. Okay, so this is our diagram. Right, so that was marking 4.2.2. Calculate the bending moment growth and bending moment diagram. Then moving on to 4.3. 4.3 is saying calculate the position of the centroid from MO of the lamina shown in figure 2 below. Okay, so first things first, we may want to calculate the area A. So this is A1, this is A2, this is A3. These are the ones we have. So we want to calculate. Let us start with A1 first. That's a rectangle there. So calculating its area, it's 200 multiplied by 220. And that in turn gives us 44,000. Right. Then we want X bar 1. Right. The X ordinate of the center here, of the centroid. So this is going to be given by directly for a rectangle. It's going to be given by 200 over 2. And that results in 100 millimeters. That's our X bar 1. Then moving on to A2. A2 shall be given by the area of this, that's 250 multiplying 400. So of course, that's the length we've been given here, multiply 400. And that in turn gives us 100,000 square millimeters. Okay, so then it means we now want X2 bar. or x bar 2, right? It's going to be given by, of course, here we know that it's going to be 250 divided by 2, but we need to add from where it's coming from, right? From here up to here. This, so it's going to be 200 plus. So it will be given by 200 plus 250 over 2. And that in turn gives us 325 millimeters. Right, moving on to A3. A3 is 300 multiplied by 90, and that in turn gives us 27,000 square millimeters. So this was square millimeters, of course, and this was square millimeters as well here. Right, so moving on to X3 bar, the centroid X ordinate of this center here is going to be given by 200 plus. So we are considering now from this point right up to the center of this. So it's going to be 200 plus 250 plus 300 over 2. And that in turn gives us 600 millimeters. So we have them all. Now that we have them all, we go to the formula. It means X T bar is now given by A1 times X2 plus A2 times X, okay, A1 times X bar 1. That's what we're supposed to do there. Plus A2 times X bar 2, right? Plus, what else? A3 times X bar 3 over A total. Okay. So basically we are saying 44,000 that we put multiply by 100 plus 100,000 multiply 325. That's what we got there. Plus 27,000 multiplying 600 divided by 171,000. And that in turn gives us 310.527 etc. So that's 310.526 millimeters to 3 decimal places. Moving on to question number 5. Okay, question number 5 is saying, calculate the force exerted by the ram at the hydraulic slam. If an effort of 300 Newton is applied to the lever of the hydraulic press, the mechanical advantage of the lever is 15 and the efficiency of the press is 91%. The diameter of the plunger is 0.1 times that of the ram. Okay, so how do we go about it? First things first, we may want to calculate the force of the plunger. From the formula, mechanical advantage is equal to force of the plunger over the force of the handle. As a matter of fact, let it be known that the force of the handle is apparently also the effort. It is basically one and the same. This simply refers to the input force you normally apply to operate the machine. That's the force of the handle, that's the effort. Okay, so making force of the plunger the subject here, it means mechanical advantage times what? Times the effort. So what is that giving us? It's giving us 15 multiplying 300. So multiply 300. What do we end up having? 4,500. Okay, so that's 4,500 basically. Okay, now we want to calculate the ideal weight of the ram. Why am I calling it the ideal? Because the machine, we were told that it has an efficiency of 91%. That means that's where the actual weight is going to be. So calculating the ideal weight, we are saying weight over the diameter of the ram squared is equal to force of the plunger over the diameter of the plunger squared. Okay, but we have been told that the diameter of the plunger is equal to 0.1 times the diameter of the ram. That's what we have been told. The diameter of the plunger is 0.1 times that of the ram. Okay, so it means, therefore, we can substitute D for D, uppercase D, the diameter of the ram. Right, let us try to square here both sides. If we square, we are going to get 0.01 D squared, meaning to say the square of the diameter of the plunger is now equal to 0.01 D squared, the diameter of the ram. Right, so with that in mind, we can now go into substituting that information. W over D squared is equal to 4,500. That's the diameter of the plunger we have just determined, divided by D is 0.01 D squared. That's lowercase d there. Okay, so making a W the subject, it means we are simply saying multiply by D squared, multiply by D squared, then what do we get? Of course, maybe you can just cross multiply and divide again. I kind of think it wastes a little bit of time if we do that. So we just make W the subject directly by multiplying myself. So we have D squared times 4,500 divided by 0.01 D squared. D squared and D squared, they cancel each other, which means W is equals to 4,500 divided by 0.01, and that in turn gives us 450,000 Newton. What is that marking? It is marking the the ideal weight. You know, when a machine is said to be having an efficiency of 91 of a certain value, it's really correct to say that there is no machine indeed that can be an ideal machine, meaning it's operating at 100% efficiency. It's not possible. So with that in mind, we now have the ideal weight. Now that we have the ideal weight, the next thing that we may want to do is to now calculate the actual weight of the ram. And we are going to get it from where? The actual weight is now going to be given by 450,000 multiplying 0.91. And that in turn gives us 409,500 Newton, or we can write it as 409.5 kilonewton, to be correct when we say that. Okay, that becomes the actual weight. Okay, 5.2. 5.2 is saying a single reciprocating pump has a piston with a diameter of 0.6 meters and a stroke of 0.3. The water is lifted through the vertical height of 15 meters. The pump speed is 15 revs per minute, and the actual quantity of the delivered is 65.1 liters per second. Calculate the percentage slip of the pump. Okay, first things first. Now that we have the actual quantity, the actual volume of the pump, we may want to calculate the theoretical volume, because the actual volume was determined when the slip was included. It is so. What do? We calculate the theoretical volume, because percentage slip is actually equivalent to the theoretical quantity minus the actual quantity that we apparently have there, divided by the theoretical quantity times 100. That's the percentage slip. We can find it with that. So in calculating the theoretical quantity, QT, I'm going to call it QT here, it's going to be equal to area times length times the speed. So we can normally use this abbreviation here and it will still be correct. Okay, so simply put, we are saying we want the area pi d squared over 4 multiply by the stroke length multiply by the speed. Of course, the speed must be in revs per second. Right now it is in revs per minute, 50 revs per minute. Okay, so substituting what we have, pi multiplied by the diameter, and our diameter indeed it is given as in 0.6. That's the diameter we have been given there of the piston. Okay, so that's 0.6 squared multiplying the length, the stroke length 0.3 multiplying the speed 50, right, divided by 4 times 60. Why 60? We want to convert the revs per minute to revs per second. Okay, so when we punch that, we get 0.07068 etc. 0.68 cubic meters per second. We want it in liters, so what do? We multiply by 1,000. 1 cubic meter is equivalent to 1,000 liters. So multiplying that by 1,000, we end up having 70.686 liters per second. This is what we now have. Okay. So we can now therefore use it to calculate the percentage slip. We said percentage slip is equal to QT. We have it now 70.686 minus QA. We have it before, that's 65.1 over 70.686 multiply that by 100, and that in 10 gives us 7.90255491. That's 7.903% to 3 decimal places. Okay, that marks our percentage slip. Let's go to 5.2.2. Calculate the theoretical power. Apparently, yes, the theoretical power required to drive the pump. Power is equal to density multiplied by gravitational acceleration multiplied by the theoretical volume multiplied by height. Why? Because we want the theoretical power. So density of water, let it always be known that the density of water is 1,000 kg per cubic meter, right? So that's our density there. So in this case, it's 1,000 multiplying 9.8 multiplying, right? Our quantity must be in cubic meters. So it's 0.070686 multiplied by the height 15. Now to change it to right now, it is in cubic meters, the way it is. So if we are to use, for example, the first one, which was the one we just got theoretical quantity, which was 70.686, we could have just divided that by 1,000, and it means therefore we're simply going to say 9.8 times the 70.686 times 15. We are still going to arrive at the same answer, which is 10.391 kilowatt. Right, so I'm trying to say we could have just said power is equal to, now if density is included, which we said is 1,000 multiplied by 9.8 multiplied by 70.686 over 1,000 multiplied by 15. It means this 1,000 and this 1,000 are cancelling each other. 9.8 times 70.686 times 15. We're still going to arrive at the same answer, which is 10.391 kilowatts, 10,390.842 watts. That's what we are having there, right? So that is now taking us to 5.3. By the way, we are saying the density is kg per cubic meter. That's the SI unit there. Okay. Calculate the work that may be done. Okay, I'm erasing the board. Calculate the work that may be done by water from a dam that is 101 meters above a water turbine. The pipe leading to the turbine has an internal diameter of 0.9, and the density of water is 1000 kg per cubic meter, and the gravitational acceleration is 9.8 square meters. First things first, we'll calculate the volume from the formula pi d squared times h over 4. So from what we have right now, pi multiplied by the diameter 0.9 squared, multiplied by the height 101 over 4, and that in 10 gives us 64.253 cubic meters. Okay, then using the formula mass is equals to density times volume. It means the density 1000 multiplied by the volume 64.253, and that in 10 gives us 64,253.42375. And therefore, it means the the work that must be done is actually apparently equivalent to the gravitational potential energy, to the potential energy, in fact. So it means the mass that we just calculate 64,253.42575 multiplied by 9.8 multiplied by 101, and that in 10 gives us 6,359,800 apparently 63,598 and 38.83. That's the value we are seeing on the calculator, which if we just press the EMG button, it's going to give us 63.598 times 10 to the power of 6. That means it's mega joules. That marks the work done. Okay, so that's 5.3 for us there. That is now taking us to question number 6. Right, a tensile force of 25 kilonewton is applied to a rectangular bar 12 millimeters thick and 22 millimeters wide. The original length is 1.8 and Young's modulus for the steel is 195 gigapascals. Calculate the stress 3.6.1.1. First things first, we want the area 12 multiplied by 22. That's the area there, 12 millimeters multiplied by 22 millimeters. And that in 10 gives us 264 square millimeters, right? And then stress is going to be given by the way, this symbol here is the lowercase symbol for sigma, the Greek letter sigma, lowercase sigma. So it's equal to F over area, force over area. So our tensile force 225, so we simply say 25 times 10 to the power of 3, that's kilo there, divided by the area, 264 times 10 to the power of negative 6 to change square millimeters to square meters. So let's just be known that when you want to change square millimeters to square meters, multiply by 10 to the power of negative 6. Or alternatively, you could have changed these millimeters already to meters. Then you calculate and you find your answer already in square meters. Okay, so what are we getting then? We are getting 94.697 times 10 to the power of 6 pascals. That means it's 94.697 megapascals. That's 6.1. Moving to 6.2, the final length of the bar. Right, so in calculating the final length of the bar, first things first, we are using the formula Young's modulus is equal to stress over strain. Right, so making the strain the subject, it means stress over Young's modulus. We can find the strain. So that means we have 94.697 multiplied by 10 to the power of 6 divided by what are we having is the Young's modulus, the 195. So that's 195 times gig, that's 10 to the power of 9. So it's giving us 10 to the power of 9, which in 10 gives us 0.486 times 10 to the power of negative 3. Okay, so with that, we are now saying, but strain is equal to delta L over the original length. So it is changing length over the original length. Okay, so making the change in length the subject. Delta L shall therefore be given by original length multiplied by the strain that we just got there. Apparently, that is going to give us 1.8. That's the length we were given. Multiply 0.486 times 10 to the power of -3. That gives us 8.748 times 10 to the power of -4 meters. That is the change in length. But the final length is what the question was asking. So final length is therefore equal to the original length plus the change in length. So 1.8 plus 8.74 times 748 times 10 to the power of -4. That in 10 gives us 1,8008748, which is 1,801 to 3 decimal places. That marks our 6.1.2. Let us go to 6.2. 6.2 is saying figure 3 below shows a round steel rod subjected at a tensile load of 55 kilograms. Young's modulus for the steel is 200 gigapascals. Calculate the following. Number one, the maximum tensile stress. Right, so first things first, we want A1, the area. It's going to be given by pi multiplied by g squared minus g squared over 4, right, where g squared, the uppercase g squared is going to be 50, right, minus the lowercase is going to be 25 over 4, and that in turn gives us 1,472.622 square millimeters, right? Remember, whenever we want it in meters, we just say times 10⁻⁶. Okay, so therefore, maximum stress is equal to F over A1. Then it's going to give us 55 times 10 to the power of 3, they said kilonewton there, divided by 1,472.622 times 10 to the power of -6. And that in turn gives us 37.348 megapascals. That now serves as the maximum tensile stress. So it takes us then to the minimum stress in the rod, 6.2.2. A2 is going to be given by pi g squared, and that gives us pi times 50 squared over 4, and that is 1,963.495 square millimeters. Okay, so minimum stress is going to be equal to F over 18. So that 55 times 10 to the power of 3 divided by 1,963.495 times 10 to the power of -6. Remember, we want to change it to square meters. So in 10, it's going to give us, that's 2,880,000. So let's just directly 28.011 times 10 to the power of 6. That's our stress there. Okay. Now, the next question is now saying calculate the total strain. Okay. First things first. We may want to know the first section strain. So this first section, the strain is going to be given by, okay, that's going to erase here. So at first section 1, which one is it? The one where we are having the maximum stress, of course, over our E1. So we are saying over E, the Young's modulus. We apparently do have it there. So what did we calculate as the maximum stress? We got it as 37,348 times 10 to the power of 6. Divide by Young's modulus, we were told is 200 big there. So it's times 10 to the power of 9. Okay, that's what we have been told, 200 gigapascals. That's Young's modulus. Okay, so it means therefore E1 shall therefore be given by 1,867 4 times 10 to the power of -4. Okay, at section 2, it means again E is equal to minimum stress over strain 2. So making that strain 2 the subject, it means we are saying stress mean divided by E, Young's modulus. So that in 10 is going to give us what? It's going to give us 28. Remember, the minimum stress, we got it as 28.011 times 10 to the power of 6. Divide that by 200 times 10 to the power of 9. That in 10 gives us 1,401 times 10 to the power of -4. Okay. Now, therefore, E total is now going to be given by 1,8674 times 10 to the power of -4 plus 1,4. This value actually before you round is 0055. So we may use that which is not rounded off directly, 0055 times 10 to the power of -4. And that in 10 gives us 3.264 times 95 times 10 to the power of -4, which 3.267 times 10 to the power of -4. Or we can write as 326.795 times 10 to the power of -6 will still be correct. That marks the total. Okay, that takes us to question number 7. Question number 7 is saying first, describe the isothermal process. So it is a thermodynamic process in which the temperature of the system remains constant throughout. This is a thermodynamic process in which the temperature of the system remains constant throughout. Right, a right rectangular prism of the cast iron has dimension 55, 45, and 35 millimeters at 25 degrees Celsius. The prism is heated at 88 degrees Celsius. The coefficient of linear expansion of the cast iron is 9 times 10 to the power of -6 per degrees. Okay. First things first, calculate the following: the increase in volume. Okay, so first things first, the original volume is going to be given by 55 multiplied by 45 multiplied by 35, the dimensions that we've been given, which in turn gives us 686, that's 86,205 cubic millimeters. Okay, then changing volume is going to be given by that's gamma multiplied by original volume times changing temperature. Right, that's our T there. Okay, but we have been given, this is the coefficient of volume expansion. But what we have been given is the coefficient of linear expansion. As a matter of fact, that coefficient of linear expansion can give us the coefficient of volume expansion half by multiplying it by 3. So simply say 3 times 9 times 10 to the power of -6, multiplying the 86625 that we have multiplied by the change in temperature. Temperature change from 25 to 88. So that's 88 minus 25. Okay, and that gives us 147.349 cubic millimeters. That's what we have there, 147. 147, I just want to write it nicely there, comma, 349 cubic millimeters, okay? Right, so now we want 7.2 to the volume of at 88 degrees Celsius. So the volume at 88 is simply going to be given by the original volume plus the change in volume. So we simply say 86,625 that we have plus 147. So it's actually 147,349. And that in turn gives us 86,772.349. Right, that marks our volume to 88 cubic millimeters. Okay, 7.3. The next question is now saying determine, of course, the volume of the gas at 270 degrees Kelvin, increased by 0.29 cubic meters. If the temperature increases by 70 kelvins, calculate the original volume if the pressure remains constant. So in this case, we can use Gauss law, V1 over T1, since pressure remains constant is equal to V2 over what? Over T2. Okay, so we can substitute, but we don't have V1. We apparently have the change in the volume. So since we have the change in the volume, it means V2 is simply equal to V1 plus 0.29. So we can take that apart. So it means V1 over T1 270 is equal to V1 plus 0.29 over 270 plus 70, that's 340, right? So making V1, the subtract cross multiply there, V1 times 340 is equal to 270 multiplying V1 plus 0.29, okay? So that in turn gives us 340 V1 is equals to 270 V1 plus 270 multiplied by 0.29, that is 78.3. Okay, so transposing, it gives us 340 V1 minus 270 V1 is equal to 78.3. So this is 70 V1 is equal to 78.3. Divide by 70, divide by 70. So V1 is equal to 1.11857,142. That's 1.119 cubic meters. That marks our V1, the original volume. Right. So it takes us then to the next question, which is 7.4. 7.4, the pressure volume diagram of the two gas processes is shown in figure 4. Study the diagram and answer the question that follows. What is the process from B to C called? Apparently, that's from B to C. That's an isochoric process. And an isochoric process is when pressure increases. It can increase or decrease due to temperature changes. So it's basically one and the same. So that's an isochoric process there that is being indicated here, right? That's 7.4.1. 7.4.2, calculate the total work done by an ideal gas in the process A, B, C. Right, so it might interest us to know that work done is equal to area under the graph. So looking at the shape that we have here under the graph, this is a rectangle together with a triangle. So we'll simply say area of the rectangle plus the area of the what? Of the triangle. That's what we are going to use. So we simply put What is the distance from this point to this point? That's 1, 2, 3, that's 30. So that's 30 multiplying 100. That's the rectangle there. This is the rectangle that I've just calculated its area. Plus, we now have a right angle triangle there on top, half base perpendicular height. So it's half of 30, multiply again by 100, because this length here becomes 100 as well. So what do we get? We have 3,000 plus 500. 1,500, sorry. This is giving us 1,500. So what do we get? We get 4,500 kilo joules. That marks our work done there. We have arrived. So that's what we're supposed to do. They're constituting a total of 100 marks, and this is marking the end of the revision of the paper. Kindly subscribe to the channel for more of these revisions that we shall be doing, as well as more tutorials and questions relating to engineering science as well as other areas.